All right. So previously, we were talking about these aldol reactions, and we had said that if we put a strong base in the presence of an aldehyde or a ketone, we can deprotonate that alpha hydrogen, and we can generate the enol or the enolate. I should really say the enolate. We can generate the enolate intermediate there, and that acts as a nucleophile and can attack another carbonyl, and we can start to condense or bring together two different aldehydes or ketones and aldehydes. And sodium hydroxide works, or some kind of alkoxide, ethoxide, something like that would work also. LDA is kind of the way to go because it. So here's one of the things, right? We're doing chemistry on paper, and chemistry on paper is a little bit different than chemistry in the lab. LDA will irreversibly form the enolate, right? It'll just, it'll establish the equilibrium there. There's no reverse reaction, these kind of things, as long as we do the proper setup. And I'm not going to sit here and talk about why or how or do dropwise additions and this kind of stuff, but we can use LDA. What I want to say is we can use LDA to control our enolate formation. That's really what I want to say with it. So usually we'll see these things done with LDA. So what we had talked about is, what if we want to mix some asymmetrical ketones or aldehydes together? What if we have these two here? Let's do one in blue, and let's do one in red, right? So let's say we wanted to mix these two together for whatever reason, because we're under quarantine and we got nothing better to do, so we wanted to just mix these together, right? Well, if we just put both of these together in a vial, right, or a reaction flask or whatever it is, and just added some not LAD, added some LDA, right? If we just added some LDA, and then we heat this up, or we heat this up or do whatever we need to with it, we would, end up with a big old mess, right? Because, right, there's a lot of different positions, right? These two green those two green carbons could get deprotonated. This black carbon could get deprotonated. What color have we not used? Green, let's see, purple here, right? This purple carbon could get deprotonated. And now, obviously, there's going to be a preference for some over the other, but any of those could get deprotonated, form the enolate, act as a nucleophile, either attack another red molecule, attack a blue molecule, right? We would get a lot of different products out of this. So this is not really a good way of of trying to make a selected product. What we would want to do instead is we would take our acetone there, our blue molecule one, right? Put some LDA into there, okay? And then we would want to come back and add our ketone or our aldehyde or whatever it might be, and warm it up, okay? Because here's what's going to happen. As in the first step, right, we're going to generate the nucleophile, right, the enolate. And then we've got a solution of that floating around, okay? And then we would add in our ketone here, or our aldehyde, right? And that would form the product that we were going to, or a more selected product, I should say, right? So that was red, right? That hits that carbon there, right? So we would form that, okay? And then if we finish this up, right? If we finish this up with some acid work up here, right? Then we would just end up making the alcohol there, right? Good. So really, you got to be careful about, since we are doing this on paper, right? You got to be very specific about the order that you want to add the reactants into there, right? If you just put everything together, then you make a mess. But if you do a controlled addition, then you can create one product, right? And of course, if you heated these things up, right, you could, eliminate and make the double bond there, okay? Say, okay, that's fine. I understand this, and that kind of makes sense, right? Look for the alpha hydrogens, deprotonate, make the enolate, look for a nucleophile, such as a ketone or an aldehyde, and then bring those two together, right? Okay, this also works with esters, okay? This also works with esters, so let's say we've got our good old buddy ethyl acetate here. And we could put a strong base into there. We could do LDA, and that's fine. But what we could use instead is, let's put in our good old buddy, Mr. Strong Base. Okay? Now, I think you guys can see where this is about to go, right? If we've got a strong base, right, there's our alpha position, right, boom, boom. Okay, right, so we end up forming our enolate again, and of course, I hope you guys remember from the last video, right, that we are, right, I'm leaving off the resonance forms, right, because this is the one that does something for us, right, and this then, right, we could react with another equivalent of an ester. If we attack a carbonyl, right, we kick up. Alright. Let's see, I'll probably run out of room if I do that over there. So we have this, we made a black bond to another. There, right? Hopefully you guys are kind of following, right? There's the carbonyl carbon, there's the carbonyl carbon there in green, right? We open the door, then we close the door. So we have this, we have this, we have this, and then, let's see, how do I want to draw this here, right? We got that, we got this, we made a black pi bond, and then we got the red. Okay, cool. Of course, let's just clean this up here a bit, right? Let's make this look a little bit prettier. So we have this, 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 okay? And so let me just make this a little bit obvious here then, and that was black, and then that was black. Okay. Hey, that's pretty cool, right? Now we can bring together esters also. But there's a couple of important points to recognize with this reaction, right? In essence, the mechanism is exactly the same that we've seen for the Aldol condensation or any of those. But this is what's called the Claisen condensation. Now, a couple of things to recognize about the Claisen condensation. One, and this has kind of been the theme for all these reactions, is what's the base that gets used? Okay, so I specifically used eth oxide here, right? I specifically used eth oxide here because you need to use the same ester group as what you have present on your esters to begin with. Okay? Because if you don't, remember, we have that issue of transester, or we can swap out our ester group. So let's do this here as a visual effect. Let's say we tried to set up this reaction where we wanted to do a, whatever there, that's fine. Let's say we wanted to set up a Claisen condensation. We used butoxide instead of eth oxide. Right? Remember that, these can easily hit the carbonyl carbon, right? We open the door, we close the door, and we kick that off. And we could end up making this ester, which could go on to react, but again, right, we'll end up making a mess, or we'll end up scrambling things, right? That ethoxide could come back in and then do a bunch of different, right? So we have to be careful of the base that's being used. You want to use the identical base to what's already attached to your ester group. So if you have an ethyl group there, make sure you bring in the ethoxide. If you have a propyl group there, make sure you bring in the propoxide. All those kind of, those kind of ideas. Okay? So picking your base, that's important. Sorry about that. I have to take care of some research stuff real quick. The second important thing is to realize that something happens after the condensation step is finished, right? So this was the product that we had from our reaction. Now, this is floating around in a very basic solution, right? So there's some of this base that's still around. And so what happens then is, remember, these alkoxides are extremely powerful bases. And so they're going to go after acidic hydrogens. Now, those alpha hydrogens to the ketones are somewhat acidic, right? That's a fair statement. But there are far more acidic hydrogens. And it happens to be that those hydrogens here in the middle are pretty darn acidic, okay? In fact, I think they've got a pKa of about 9-ish or something like that, if I remember correctly. It depends a little bit here, right? But I think a pKa of about 9 is a pretty fair assessment. I could be off by a little bit here, but I'll see if I can come up with a specific number for you guys. The point being, they are very acidic. So what actually happens at the end is that our product really is this, right? Now, that has a couple practical aspects for us. One, that could be useful, right? We've generated a fairly soft nucleophile, right? We've generated a fairly soft nucleophile here, and it will be as a nucleophile, and we can do something with that. So we'll learn a little bit about those kind of reactions coming up. But also, right, if we want to work up this product, we need to come back and reprotonate everything. So when we set up this reaction, make sure that you finish with some acid workup also, okay? And that'll take care of protonating this, right? And it'll take it back to the protonated form there, okay? So put in a strong base, let it do its thing, and then finish with an acid workup. All right. And so there's our Claisen condensation. So kind of works the exact same way as with the Aldol condensations and all these kind of things, right? You can use LDA for this also. That'd be just fine, right? You can use LDA for this, and then we can kind of avoid the issue of swapping out the ester and that kind of stuff. Yeah, and I think, I think this is a good stopping point, okay? So there's our ways that we can start to clip together different carbonyl groups, aldehydes and ketones and esters. And the important part is to think about the order that you do things, right? We generate the enolate, and then we put in our nucleophile, and we can control the reaction in that way, right? We can also control the reaction by not having any alpha hydrogens. And what I mean is this, right? Let's say we wanted to do an aldol condensation with acetophenone, right? We only have alpha hydrogens here in red, okay? So that's going to control our reaction. If we have our buddy benzaldehyde, for instance, right? Benzaldehyde, we don't have any alpha hydrogens, so we don't have to worry about, setting up an enolate or anything like that. That's, these things are going to just, exist as they are under basic conditions, well, depending on what the base is, right? But I think you guys get the idea, right? So controlling the addition of things, controlling whether we have alpha hydrogens or not, that's going to be something that's going to help us predict what the reaction is going to be and control what our products will come out of this, okay? All right, in the next video, we'll talk about kind of a continuation by alkylating alpha positions, and so I think you guys can already see what we're going to do, right? But we'll We'll talk a little bit more about that when we get to in the next video there.